Hey guys, welcome back to Notes with Griff. Today we're talking about 14.3, the rate law. This is our effect of concentration on reaction rate. And as far as AP goes, this is probably one of our most important sections. So you want to start this one. You really want to get this one because this is where the questions for AP Chem will come in. And when we get to those questions, I will definitely make sure to let you know which ones those are. So let's just jump right in. We've got the rate law, the effect of concentration on reaction rate. So in the last section, we talked how to calculate rate. And here we're going to be talking about what to do with that rate once we calculate it. So rate law is basically the relationship between the concentration of a reactant and the rate of the reaction. So basically we're going to see how does one of the reactants affect the rate of the reaction? Does it speed up the reaction? Does it slow it down? Does it have no effect? That's what the focus of this section is on. So take the generic reaction, A goes to products, just a very simple one. The rate law for that is K times the concentration, remember brackets mean concentration, to the power of N. So K is what we're going to call the rate constant. And the rate constant is constant for that reaction at that temperature. So no matter how much you have, that's our rate constant, obviously, because it's constant. And so it's always constant until we change the temperature. And we'll get into that, I think, in section 14.5. So now, moving on to this exponent N. N is an exponent, and it's how the reaction is affected. And the key here to see that's going to be very important is that N does not show up in the reaction. There's no N there. It's not like a stoichiometry thing. There's no N there, all right? So don't think of that. You have to determine N experimentally, all right? So let's talk about reaction orders and what they mean. If N equals 0, the reaction is 0 order. And so that means that the rate is independent of the concentration of A. And if we write our rate law out, you'll be able to see that. Granted, there's one down here for it. But so we've got rate equals K times our concentration of A raised to the 0 power. And we know anything raised to the 0 power is 1. So that way the concentration of A is not affecting. If N equals 2, the reaction is first order and the rate is directly proportional to the concentration of A. So as A goes up, our rate will go up. If N equals 2, the reaction is second order and the rate is proportional to the square of the concentration of A. And we'll talk about that a little bit more down here, so just hang tight on that. Hopefully you're understanding that. Now here's something that I want you to key in on. Other orders are possible, including non-integer orders. These are the most common. So our most common are 0, first, and second. But there are other orders possible. I have seen on AP questions a reaction order of a -1. I've also seen to the 1/2. So we want to be aware and make sure we know how to do it and we're not just guessing. Okay, so our three most common reaction orders, N equals 0, 1, and 2. If you have a 0 order reaction, this is what we kind of alluded to in B. Rate equals K times A to the 0, which just equals K. So our rate equals our rate constant. Our concentration of reactant decreases linearly with time. The slope is constant, basically indicating a constant rate. So what we're saying here is this one is unaffected by amount of A. All right, unaffected by the amount of A. Our first order reaction, which is a reaction order of 1, that's rate equals K times the concentration of A raised to the first power. The rate slows down as the reaction proceeds because remember we said as the reaction proceeds, the amount of our reactant is being used up and so it decreases, so thus slowing the reaction down. And our rate is directly proportional to the concentration. On to our second order reaction, rate equals K times A to the second power. Our rate is proportional to the square of the concentration, as you can see there. And remember, K stays constant, so yeah. Moving on. Again, I think we've already said this, but it's very important to say again. Our rate or our order can only be determined by experiment. One way, the most probable way that we'll use in AP Chemistry is finding the rate law based on initial rates. What they do is they have a reaction, they test how the reactant concentration changes over time, and then they give you that information. So how do we use them? We look at the concentrations, how they change over time, and we're actually going to be setting up a relationship, and I'll show you how to do that when we get to our practice problem. Now, most of the time we want to know each reactant, and most of the time there's more than one reactant, so how do we do it for multiple reactants? Basically, we add up the two and figure it out from there. So let's look at a generic equation. This generic equation is the one that we're going to use throughout our examples, so it's kind of important to look at. So we have here a generic reaction, little a, big A, plus little b, big B, goes to little c, big C, plus little d, big D. Our rate law is rate equals K times the concentration of A raised to the M power, B to the N power. M and N are determined experimentally, and so the overall order is just the sum of the exponents, which would be M plus N. And these exponents, or the reaction order, we're going to talk about in another section, but it determines the molecularity of a reaction, so just kind of put that in your brain and hold on to it until a later section. Okay, so let's figure out how to do this. Example 14.2 says, consider the reaction between nitrogen dioxide and carbon monoxide as written below. The initial rate of the reaction is measured at several different concentrations of the reaction